Fair warning, this lecture is math heavy, so I'm sorry if it's a bit dull and lacking in actual concepts, but I'm hoping it will help with walking through the process of these derivations. So if you end up forgetting the shortcuts, you can still come to them on your own or verify them on your own. So we've gone over the various equilibrium constants and how they're expressed mathematically. To recall, for a given reaction, let's call it reaction 1, we have the equilibrium constant Kc here. So for simplicity's sake, I'm going to say right now that for this reaction, A, B, C, and D, all lowercase, are equal to 1. So that's going to simplify our reaction and our equilibrium constant as such. So now my question is, what happens if I write the reverse of the reaction above? And we'll call that reaction R for reversed. And now the products and the reactants are flipped. So how would that affect the equilibrium constant? Well, let's write the K expression for that reaction called Kr, and we'll compare. We can see here that the equilibrium constant for the reverse reaction, Kr, is actually the inverse of the original equilibrium constant, K1, as in the numerator and the denominator are switched. So we can add that to our quick references, right, where the opposite reaction leads to an inverse K. All right, what about if we multiply the entire reaction? Say this time all chemicals have a stoichiometric equivalent of 2. So reaction 2, we'll call it, looks like this. And that makes our equilibrium constant for that reaction like so, which now looking at it back at our original equilibrium constant, right, we can see that K2 is actually just K1 squared. So you can try this with other multiples or even fractions, but you'll see the same general result, that when you multiply a reaction by n, the new equilibrium constant is k to the nth power. These manipulations are pretty straightforward and easy to recognize, but what about when things get a little more complicated, right? If we start adding different reactions together, I'm going to introduce a few more reactions here, down below, and we'll call them reactions 3 and 4, and they're drawn there. And so my question is, how are these three reactions, reactions 1, 3, and 4, related? Some have more or fewer products and reactants, and some have different chemical species altogether. So it's kind of hard to see the relationship at first. But we can start by looking for the most unique similarities. So we can see that both reactions 3 and 4 have E in the product, while 1 does not. So what that tells me is that either reactions 1 and 3 can be added together to get 4, or reactions 1 and 4 can be added together to get 3. But I'm certain that reactions 3 and 4 can't be added together to get reaction 1, because that would result in 2 molar equivalents of E in the products, and we know that reaction 1 has no E in it at all. So we can try out my options that I proposed above, right? If I add reactions 1 and 3 together, then we get this big reaction here, which doesn't look like reaction 4 yet, but we can simplify it by removing any redundancies that occur on both sides. For example, because we have 1 molar equivalent of D in both the products and the reactants, they cancel each other out. And the same goes for B. Then we're left with 2 equivalents of C in the reactants and 1 in the products, so we can remove 1 C from each side. And when we rewrite that all cleaned up, we see that we have reaction 4 again. But how does that translate to the equilibrium constants? Well, let's write out all of the constants, which we already have up here for reaction 1, but reaction 3 has equilibrium constant K3 drawn as such, and then K4 has it written there. And so again, there doesn't appear to be an obvious connection here. We can also look at the K constant for the massive 1+3 reaction, which remember is the same reaction as reaction 4. So K is going to be technically equivalent as well. And when I write out the products over the reactants for that big reaction, then we can see that it's actually equal to K1 times K3. And so this trend can be summarized as such, right? When you add two reactions together, the new K constant is just the product of those equilibrium constants. So in summary, the reverse reaction results in the inverse K constant. Multiplying the reaction results in K, or to the power of that scalar, and adding reactions together results in the product of their K constants.